The ICOR project is about introducing cognitive management technologies for the Internet of Things in order to tackle the heterogeneity of objects and devices and the complexity that comes with the huge number of objects that is envisaged in the Internet of Things. So, building on previous research efforts in ICOR, we have defined a cognitive management framework that comprises three different levels of functionality. So at the bottom level we have the so-called virtual object level, where we have virtual representations of real-world objects. Real-world objects can be devices such as sensors and actuators, but also any object that has a virtual identity. The next level is the composite virtual object level, where we have combinations, mashups of different virtual objects, in addition with some service logic that adds additional intelligence to the virtual objects. And the top level is the service level, where there is functionality for real-world knowledge modeling and growing, which is exploited for dynamic service deployment in the Internet of Things, also taking into account user and stakeholder requirements that can be mapped from high-level requirements to more technical requirements through service request analysis that also exploits real-world knowledge.
Starting from the service level, we have a graphic user interface that allows the user to interact with the ICOR system. From this user interface, the user is able to select the device where the desktop, where the CBO application will be instantiated. In addition, can set the service request in natural language, expressed in natural language, while can select a set of different policies for the request CBO, such as energy efficiency or high quality, or can select all these policies. After that, can provide the service request to the natural language processing mechanisms and service analysis mechanisms in order to provide to analyze the request in the form of parameters that are understandable by the system, and these mechanisms are hosted in this machine.
Okay, and here we have the natural language processing mechanism. Its objective is to receive the service request and to derive a set of functions that correspond to this service request. So for this purpose we need a set of service templates that at the ICOR system the domain experts create and design. For this operation we use the WordNet dictionary, node-based algorithms, and we exploit the Bayesian networks. So the output of this operation, we can see in the screen that we have a set of functions that are picked, like the environmental temperature, the outdoor lighting, the body pulses. The virtual objects that will be selected to compose the CBO need to fulfill to offer these functions.
So having functions that are included in the selected service template, we provide the service execution request to the CBO level so as to create the CBO. More specifically, the service request goes to the approximation to the user opportunity component, which initially looks into the CBO registry so as to find another existing CBO that could fulfill the current service request. Currently there is no matching, and for this reason this component will forward the service execution request to the CBO composition engine in order to create the CBO from scratch. And this component is hosted on this computer.
Okay, and here we have the CBO composition engine, and its objective is to evaluate the available virtual objects in the area of interest in order to compose an optimal CBO. This selection will be based on the requested functions and the requested policies. So here we can see the list of the available virtual objects in our area. Each virtual object may offer one or more than one functions, and the utilization of each of these functions is characterized through a set of features. For example, we have the quality, the performance, the security, the consumed energy. For these features we have values like low, medium or high. So the optimal CVO will be based on these values, and it's an optimization problem. We have an objective function and a set of constraints. Solving this optimization problem, we receive as output a set of virtual objects and functions of these virtual objects that maximize the value of the composed CVO. Afterwards, we have two more steps. The first one is to store the composed CVO at the CVO registry in order to reuse it for future requests, so not to repeat the same operation. And finally, to activate the composed CVO.
The measurements of the environmental conditions that are received by different sensors that are available in the smart home. The user interface of the CVO allows us to set our preferences for various measurements. For example, if we change the threshold of the temperature measurement, the air conditioning system in the home is activated. The same can happen when we change the luminosity threshold. We are changing the threshold. We have the lights that are turned on in the home. Based on the self-management capabilities of the CVO is able to detect a broken virtual object that is included into its composition. For example, we have a luminosity sensor that is already included in the composition, and if we unplug the sensor of the platform, such that the CVO detects that this sensor is broken, and for this reason, pressing OK, it will request from the CVO composition engine to provide another one virtual object with the same function so as to replace the broken VO. Initially we have an information message there that informs us about the broken virtual object, and pressing OK, we have the CVO composition engine.
And now the CVO composition engine repeats the same operation as previously in order to evaluate the available alternative virtual objects that may offer the function that was malfunctioning. So here we find only one alternative that offers us the ambient luminosity functionality in order to sustain the functionality of the composed CVO.
Information message that the CVO has received the new virtual object that will replace the broken virtual object. There is a change here from the previous VO to the new one VO, while another sensor that is included in this composition and represented by a virtual object is a motion detection sensor that is available, that is included here in this box, and is able to detect the move out of the home. Based on the sensing of this sensor, the CVO is able to detect if somebody is outside of the home and tries to cross the road. And for this reason, the CVO sends a command to the smart traffic light CVO in order to be red for the car so as the pedestrian to cross the road. And my colleague will continue with this concept.
Okay, and now we are going to demonstrate the coordination mechanism. We have the smart home CVO that we just created. We have the smart car CVO that controls and manages this car. We have the smart traffic light CVO. So as you can see on the screen, the smart home CVO will send a command to the smart traffic light CVO in order to request for a green light for the pedestrian and a red light for the car. At the same time, the smart car CVO will request for a green light, so the smart traffic light CVO will have to request from two different entities that of course cannot be satisfied at the same time. So it will identify that there is a conflict and will trigger the coordination mechanism in order to resolve this conflict. So for our CVOs we have features and weights. It's an optimization process to decide which one has the highest priority. In this case, the pedestrian will have the highest priority and will cross the road first. So here we can set our car in an automatic mode, so it will start. And there the motion detection sensor will identify that the man is trying to cross over, so we have a red light for the car, here a stop message, and the car has stopped, and the man is allowed to cross the road. Afterwards, when he's on the other side, okay, we can continue, and we identify that he crossed the road, so the car is still waiting, having a stop message, and okay, and now we have a go on message for the car to continue.